Welcome you all. So now we are module 1, lecture 2. We are going to discuss what is free body diagram. What is a free body diagram? The rigid bodies or a system or a mechanism or a machine is consisted of or consisting of different components. Okay, we may be interested in only one component. Say for example, you take IC engine. In IC engine you have piston, connecting rod and crankshaft. So that is represented as, you take this as piston and then a connecting rod and there is a crank as well. So this is the crank and okay, this is connecting rod and this is piston. This is a system, a mechanism. Okay. Now, free body diagram. How to draw a free body diagram? What is a free body diagram? Free body diagram. First, we have to isolate a particular component from the system. For example, I want to analyze, I want to understand the forces that are acting on a piston. So I will just isolate this piston alone and then representing all the forces that are acting on the piston, not by the piston, on the piston. So what are all the forces that are acting on the piston? Say this is the cylinder portion. Okay, you'll have a piston head here, so the valves are there, you know that. So the fuel particle are here and it is burnt here, so the fluid pressure will be acting here. So the resultant of that, the fluid force, okay, pressure is forced by area. Area is the cross-sectional area of the piston. So this force is the gas pressure. That force is acting here. Okay, and when it is supported, assume it is having contact on the surface of the cylinder. Okay, there will be a reaction. So according to Newton's third law, see, I am exerting a force on this board. The board will exert equal and opposite force on me. So if my hand is the free body, then the force exerted by the board on the body has to be represented. When I am discussing or my interest is on board, then the force that is exerted by my hand will be considered when I am analyzing the board. When I am just considering only my hand, you have to look at only my hand. So similarly, now the cylinder wall exerting a thrust force on the piston in this direction, that we call as the normal, some force. And then when it is pushing that, okay, the connecting rod, it has a mass, the connecting rod will exert a force in this direction onto the piston. Now if I have to draw the free body diagram for the connecting rod, So the connecting rod I am isolating. This is the connecting rod. I have not changed the angle. Okay, assume the same angle is maintained. Okay, so now the force that is acting on the piston, as I said, okay, equal and opposite according to Newton's third law, the same magnitude will be acting. So always the body, when it is analyzed, should be in equilibrium. We will discuss that in a minute, but for the equilibrium, so now it is balanced. Okay, now if you consider this crankshaft, the crank, okay, so this is separated, this is same point actually. So this point is represented here as well as here. Now this will give another force, okay, equal and opposite on this crank. If I have to consider the crank, my interest is crank, I will look at what are all the forces that is acting on the crank. If my interest is on the connecting rod, I will look at only the forces that are acting on connecting rod. My interest is the piston, okay, for the static analysis. Then when it is under motion, when it is F equal to ma is used, then there will be one more component, the friction will come, also the inertia force will come into picture. Let us not worry about that. These are the three external forces that are acting on a piston. We have to statically analyze the system. These are the three forces. Then what is a free body diagram? Representation of isolating the required body that needs to be analyzed, and then representing all the external forces that are acting on the body. And also, if this is some beta, I have to put that also. If at all it is considered to be a rigid body, then the size also come into picture. So the distance, this width and this height, all these dimensions you have to use. If it is considered to be a particle, then that distances will not come into picture, but the angle does involve in the calculation of the unknown forces. Okay, so to summarize free body diagram, you represent all the forces that are acting on the body. So you are isolating the body and representing all the forces acting on the body, and the reaction forces you are including. Also, if the mass is huge, you need to consider the mass, or the connecting rod masses are lumped here and here, that we will understand in mechanics of machinery course. So if I have to consider the mass, the weight is a force. If it has some mass m, then weight is m into g, that I have to put here. This completes the free body diagram. So the body force, that is the weight, the external forces, and this is a reaction force. When I am separating two bodies in contact, okay, so I will separate this body's effect on this body's effect on this body needs to be considered. When I am considering only this force, this body, I need not worry about this body. Only this body, the effect of this body and this has to be put. Okay, how that needs to be put? When, say for example, you have a rigid body like this in a slope. Okay, you are right, just you are applying some force here. Okay, so how to draw the free body for this? Okay, cylinder or cylindrical wheel. This is the surface. Okay, I will isolate this cylinder. Okay, it can be considered as a two-dimensional problem. I am going to put the, so some angle is involved. I will put in the same angle theta. I will put the direction of the force P. Now say it is having some mass. So weight, irrespective of the slope on which it is moving, the weight will always act vertically downward. Okay. Say for example you have a block moving like this. The weight has to be put always like this. Weight will be acting vertically downward. Okay. Now I am separating this body from a surface. So I am not going to show the surface here, but instead the force, that is the reaction force that is acting, or the force exerted by the wall or the surface onto the cylinder, so that will be perpendicular to the surface. Perpendicular to the surface. So perpendicular to the surface is this, perpendicular to the surface pointing to the body, because the effect of the surface onto the body I am representing like this. Now this can be thought as a particle. Okay, so I can put this in the same line here also. Here also some angle is involved that you need to put, or you may have to find out the angle also sometimes. Okay, so this is the representation of, okay, we call it a reaction force. The body force, in other words called the weight, the external force and the reaction force that are acting on the body, right, is drawn here. This representation of the forces is the free body diagram. I hope you have understood the free body diagram. When we are drawing the free body diagram to represent all the forces, we have to keep these things in mind. One is two bodies in contact. Say for example, two bodies are like this in contact. So this body is contacting the surface and the floor. This body is in contact with this surface, and these two bodies are in contact. So when we isolate the bodies, and I am isolating this body and I am isolating this body, okay, so the reaction you will put like this. Say for example this is R1, then this surface exerting a force on this body, that will put like this, okay, and then the weight will be acting downward, vertically down. So you know, when a body is in contact with another surface, another body, the reaction will come into picture, and then the weight of the body, if the mass is considerable, that cannot be neglected, then the weight is acting always vertically downward. That we have already discussed. Now this body, there will be theta as well, okay, and then this force, this body's effect on this body. Say for example this is A and this is B, then the effect of B on A has to be represented in the same line of action, okay. That means the theta, this is the angle theta. So this is the effect of B on A, and simultaneously this effect will be acting here. This is R A. the effect of RA on RB, and this happens to be equal. RA equals to RB because the magnitude is equal. So this is also theta. Okay, so when two bodies are in contact, you need to know how to represent the forces. So here also the weight will act. Maybe this is WA and this is WB, and then here will be one reaction. Maybe if it is R2 and this is R3. Okay, so this completes the free body diagram. Okay, now weight, reactions, and one more thing you have to understand. Say for example, you have a pulley, a rope, you have a weight here. So a rope is passing through a pulley. So this rope is considered to be inextensible. That is, it is not deforming. It is also rigid. So keep this in mind always. The ropes will take only the tension force. Okay? Say for example, you have to push this block this side. Can you use a rope to push this? You cannot. Okay? But using the string or the rope, you can pull it. Okay? So the rope will take only the tension force. So when you are drawing the free body diagram, the force exerted by the rope on the body is always tension. Okay, say for example, here this is the tension. Okay, in order to keep the body in equilibrium, this has to be in tension. In order to keep the pulley in equilibrium, this has to be T, right? This, it is T. Okay, this is the free body diagram for this block, and of course this is in equilibrium because of the weight. Here the weight is equal to the tension. So wherever you see a rope, you can put, right, blindly, right, the direction of the force, the sense is, okay, that is pulling the body. Okay, the tension is being active. This is one thing. Number two, when you have a rope connected, every point for a single rope, I repeat, for a single rope, every point will have the same force or the same tension. Say for example, you would have a rope passing through many pulleys, pulley 1, pulley 2, pulley 3, or anywhere it may pass. So this is a single rope. Anywhere in the point, the force is T, tension, and it is equal. Everywhere it is equal. If it is a single rope or string or wire, right, the magnitude of the force is the same. Keep this in mind when you are discussing the particle problems, equilibrium problems, or particle equilibrium problems. And when we discuss the rigid bodies, we will use some more reaction force. So supports and reactions we will be learning subsequently, or when we discuss the rigid bodies. What is equilibrium? Okay, so the summation of all the forces equal to 0. If you sum all the forces that are acting on a body, say for example the previous example where we found out the resultant force. So the resultant force was 199.65 Newton, and that was acting 4.1 degree. In the previous lecture, we solved this problem. So this is the resultant R. So it is a vector. If you are representing as vector, this has to go to 0. You had 4 forces. So F1 force vector, F2 force vector, F3 force vector plus F4 force vector, that is going to 0. If the vectors are going to 0, then the body is in equilibrium. Okay. Right? So each force, what we did there, each force will have 2 components. It will have x and y, it will have x and y, it will have x and y, it will have x and y. Okay? So to find out the right equilibrium, you can still write this as rectangular components. Okay? And then we say summation of fx equal to 0, summation of fy equal to 0. Equilibrium of particle. So equilibrium of particle will have 2 equations, summation of fx equal to 0, summation of fy equal to 0. When you are equating this, we actually get 2 equations. 2 equations. When you have 2 equations, how many unknowns you can find out? You can find out 2 unknowns. Then, for a particle equilibrium in a given system, if it is 2D, you have 2 equations, and then you have 2 unknowns can be found out. You can find out only 2 unknowns. Okay? If it is 3, if it is 1, let us discuss that in detail in the subsequent classes. Now you have to understand that number of unknowns is equal to the number of equations. Okay? So for particle equilibrium, we have 2 equations. So any given system of force, you have to reduce to these 2 equations. Now we'll solve a problem. Before that, we'll understand one more theorem called Lami's theorem. When a particle is acted with 3 forces, say for example I am taking 1, 2, 3. So all the forces are pointing towards the point. So this can be written, say for example this is F1, F2, F3, and this is alpha, this is beta, and this is gamma, the angles. This can be represented in a free body as this F2 can be put like this for the simplification. F3 can be put like this. In the same line, I have put, right? Actually, initially it was compressing the particle. Now it is pulling the particle. That means something tension that is acting. But since we are not considering we are into the particle, the shape and size is not coming to picture, number 1. Number 2, it is a rigid body, we are not considering the deformation. I have the freedom to represent the force. My F1 will be put like this. Okay? So, F1, F3 and F2. So F1 and F2, now this becomes alpha, F2 and F3 becomes beta, and F3 and F1 becomes gamma. So that, assume these are the three forces that are acting on this particle with the angles of alpha, beta, gamma. Now, what is Lami's theorem? Lami's theorem says, okay, say for example, take this force F2, okay, F2 is proportional to sine gamma. That means the angle between the other two forces. So F2 is proportional to sine of gamma. So the angle subtended by other two forces is gamma, and it is proportional to sine gamma. Then I can write F2 by sine gamma is a constant. This is what is Lami's theorem. When I write this, I can extend this with, okay, F1, the opposite angle, F1, the other two forces, the angle subtended by the sine of the angle subtended by F2 and F3 is sine beta, and F3 is sine alpha equal to constant. So this is Lami's theorem. So when you have three forces acting on a particle, this is a simple expression. Using that, I can use these two to find out any one unknown, and you can use these two to find out, or these two to find out other unknown. So it is a simplified method for the equilibrium. So the assumption is the three forces are in equilibrium. Okay, this is. Now let us solve this problem where a car is unloaded from a ship using the ropes. The tensions of the ropes have to be found out. The car weighs 3,500 Newton, and the angles are given. How to solve this problem? We'll see that now. It is having 2 degree, so this will be 2 degree, and it is a rope, so the direction is away, and we are considering this as the point. This as the particle. Okay, the car is hanging here, and the W of the car which is given, and this is also rope, a man pulling the rope, and the angle is 30 degree. Okay, I call it, so this is B, so TAB, I call it TAB and TAC. Okay, this is the free body diagram. Okay, now since there are 3 forces, in this problem I am going to use Lami's principle. Okay, using Lami's principle, how to solve this problem. So we have 3 forces, and this W is given. W is given as 3,500 Newton. Okay, this is 3,500. Okay, now using Lami, we can find out the angles. Okay, this angle is 90 degree. So the angle between TAB and TAC is 32 plus 90 122 degree. Okay, and this angle 90 minus 30, this is 60. So the angle between W and TAC is 60 degree. Okay, and the angle between these two forces are 178 degree. That's 180 degree minus 2 degree. So the opposite angles are known. Now we will be able to use the Lami's principle. What is Lami's principle? We are using W, the opposite angle, sine of the opposite angle. So W by sine 122 equals to TAB sine 60 equal to TAC sine 178. Okay, if you take these two, you will be able to find TAB. Okay, so TAB equal to W is 3500 sine 60 divided by sine 122. So TAB will be 3570 or 3 or 2, whatever value you are getting, some approximation will be there. So you can, based on the calculation, because these are degrees, directly some may calculate sine 60 and substitute there, and they may calculate. So something around this you will get. When you calculate the same way, you can use these two, or you can use these two expression to find out TAC. That happens to be the value. So 144. So this can also be solved in another way. You can make the vector addition, or the triangle we can make. So this force is here. So I can make this W, then I can bring that here. So it will have the angle 30 degree, and then this force with 2 degree. Okay, so if you take, this is 2 degree and this is 30 degree, so this is 30 degree. Okay, and of course you know this is 2 degree. Okay, so this is W, and this is the direction, and it is TAB. Okay, and this is the direction TAC. Right? Now this angle is known. What is this angle? This is 90 degree. This is completely 90 degree. 90 degree minus 30 minus 2. So this angle is 58 degree. And you know this angle is 120 degree. If you use this also, you will get the same value. How to write? W by opposite angle sine 58 degree. Okay, TAC opposite sine 2 degree, TAB sine 120 degree. We can make the triangle like this, and then we can use Lami's. The same thing can be drawn in a different fashion, because these are all vectors. Okay, just using the vector addition, I can put like this. I can put this 2 degree. Okay, and then I can put, this is TAB and this is TAC. This is 30 degree. Okay, this is 2 degree, and then this is 120 degree, and this happens to be 58 degree. So this is also possible. You can either make like this, or directly, if you know the angles, you can solve this problem. Okay, let us solve one more equilibrium problem. Okay, now we will solve this problem where a weight is hanging through the pulley and P is applied to keep the body in equilibrium in a particular inclination. So a single string is being used, which is passing through 2 pulleys, and P and alpha have to be found out. Let us solve this problem now. So in this problem, okay, what we need to find out is this alpha and this P. These two have to be found. Already we know the particle equilibrium problem. We have 2 equations. We will be able to find only 2 unknowns. Okay. Now, how to draw the free body diagram? So, though there is a pulley, I consider this as my particle. I am drawing that. Perhaps I will draw it here. Particle. Okay. And the side I will put P alpha, and this is 160 into 9.81 because it is a mass. So this is the weight. Okay, and now you see here, this is a single rope. The single rope passing through 2 pulleys and tied here. As we already discussed, when you have a single rope, all point will have the same magnitude. So the magnitude given here is P. So if I just cut and remove this, because my point of concern is this now, my point of interest is this, so I neglect that, and then already we know how to put the direction or the sense on a rope. So it is always away from the particle, and this is also P and this is also P, and I am neglecting this distance, or my interest is not on the pulley, and my interest is to find out the P. So I consider this as a particle, and then this beta is given, this angle is given, so it is coming like this. It is 2P, right? And this theta is 20 degree. It is given beta equal to 20 degree. So this angle is 70 degree. Okay. Now you can use Lami principle, or now I am going to use the equilibrium equation. I am going to form the equilibrium equations. So what is the equilibrium equation? We know summation of fx equal to 0, summation of fy equal to 0. So summation of fx equal to 0, I have to resolve this component, this forces, I have to resolve these forces into horizontal and vertical components. So if I get the horizontal component, so it is right side is positive 2p cos 70. This is summation of fx equal to 0. Okay, and then this is pointing this side, so you get p cos alpha. This is 2p cos 70. So minus, because this is pointing away, so minus p cos alpha equal to 0. Many times students forget to put this equal to 0, then they do not know what to do further. Okay, so equal to 0 has to be there. So this gives you equation 1, and then we'll make the vertical component. Vertical component will have 2p sine 70. This component will have p sine alpha. So we have 1 force, 2 force and 3 force. These are upward, so 2p summation of fy equal to 0, 2p sine 70 plus p sine alpha minus 160 into 9.81 equal to 0. This is 2. Upon solving, we get P equal to 602 Newton, alpha equal to 6.8. Is this fine? Comfortable? I hope you have understood the equilibrium equations and Lami's principle to solve the equations to find out the unknowns in a two-dimensional particle. Thank you.